So in this video, I'm going to teach you what exactly decision tree is and how useful it is, how to work with, and like what is the role of decision tree in machine learning. So everything will be covered in this session. Let me just write it down. Decision tree. You can say it is one of the most important concept, like to understand machine learning algorithms, to simplify some of the other tasks that you will be understanding in a time. So let's start from the basic, like what is a tree? So like if I want to explain it in real world examples, uh, a tree is nothing but it has many analogies in real life, and it turns out that it has influenced a wide area of machine learning covering both classification and regression. So in your machine learning, it covers both your classification and your regression. These these two topics, both the topics are covered. I have already covered in my previous lectures. If you are not still clear with them, I would request you to please pause the video and just go through the classification and regression concept once. All right. So like in daily life, we do and we take decisions, right? So in decision analysis, a decision tree can be used to visually and explicitly represent decision, and it helps in decision making as well. So as the name suggests, as the name goes, it uses a tree-like model of decision. So I'll just note down the important points. Tree-like model. Okay. So like it is widely used in machine learning, like in basically your machine learning, which will be our main focus. But let me also tell you that the decision tree, the tool which is used, is commonly used in data mining, and where it is like those who are from data mining background, they must have they must have a good understanding of decision tree, where they must be using it to derive a strategy to reach a particular goal, like whatever the strategy they use to reach a target, like make a target and how to reach that target, they use decision tree concept there as well in data mining. So in machine learning it is also important, and as well as in data mining it is widely used. All right, so like how can an algorithm be represented as a tree? So let me explain you by giving an example. Suppose, let's say, there is a patient. Okay, so this is a patient, and he went to a doctor, and he said that, doctor, I have a chest pain. Let's say he said chest pain, he is having a chest pain. So what doctor will do is, doctor will first check his BP, right? Like almost all the doctors check BP first, and then the stethoscope they use to do the heart rate and everything. So if the BP is there, like maybe a high or low, like it comes into this branch. A BP is coming into high or low, whatever it is. It He will suggest, like it will say it is a BP problem, and and I'll just tell you what will happen next. And if it's no, then he'll check, let's say, pulse. Like, sorry guys, I'm not into medical domain, I have no idea what exactly it is, but I'm just trying to explain you what decision tree looks like. So, like if you go to a doctor and you say, doctor, I have a chest pain. So he will say, okay, let me check your BP. If there is a BP low or BP yes, then again there will be two. Like there is a BP, let's say, issue. So now BP issue, BP can be low, BP can be high. If BP is low, he will suggest, let's say, drink coffee and eat salty foods, right? Whatever I know. And if BP is high, he will suggest like go for this test, or let's do a ECG as well for chest pain. And if there is no BP issue, he'll check the pulse. If the pulse is normal, once there will be a normal pulse, then he'll suggest some other thing. And if the pulse is high, he'll again suggest ECG and similar thing. I hope you're understanding. So this is what a decision tree looks like. Finally, he will be coming at a point at last, and he will be telling like there will be a result at the last, and he will get to know that what exactly is happening with the patient and why there is a chest pain. So he will get to know at last, right? So this is how, like, basically all on daily basis, like each and every of us, if we want to take a decision, some or the other way we do somewhat like this. We just don't make a tree or a flow chart like this, but we do, right? So this was the best example which I can come up with to explain the decision tree. This is how decision tree looks like. So this is just an example. So, and these are like in decision tree, these are like your root node. And also one more thing, our tree is upside down, like roots are at the top. Just make a note of this, roots are at the top and these are the leaves. So it is upside down, and this is a like root node or the parent node, and these are the child nodes that which are carrying forward at the bottom. So if I want to explain one more example, a very simple example, let me tell you. Okay, so let's say uh, like a person is going to buy a flat or a room, like not a room, or like let's a house or a flat somewhere. So he'll ask like, does this house have more than two rooms? If that flat has more than two rooms, like if there is no, like no, there is no more than two rooms, it's a 2 BHK flat. No, it's a 2 BHK flat. So your predicted price is, let's say, Christmas dollars. And yes, it is a 3 BHK flat or 4 BHK flat. Then the predicted price is, let's say, this much. So this is, again, we can simplify it, we can create more branches to it, like okay, if it's 2 BHK flat, the washrooms are attached to each room, or there is a single washroom, like this we can subdivide it. And again, so this is how decision tree can grow up, and finally like a person, he can decide like which one he can buy. So this is just, I'm giving an example how decision tree looks like, somewhat looks like. I hope, are you clear up to this? Okay, so basically decision tree naturally represents the way we make decisions in our day-to-day life, right? So this is the example which I'm showing you here right now is nothing but our decision which make we make our day in our day-to-day life. So decision tree are easy to understand, and they are the basic building block for some of the best models in data science right now. Like, there are many other methods as well apart from decision tree, but if you are very thorough with decision tree, they are like the building blocks of the one of the best project to work on in data science stream. If you are good with decision tree, you can build one best decision tree model or something. So in decision tree, like there is one benefit, like if you remember in your logistic regression, like I have explained you in my logistic regression lecture, you can only get some sort of linear boundary condition. If you, I hope you remember linear boundary condition. Let me just show you. Let me just erase this. Somewhat like this, if you remember. In our logistic regression, there was a linear boundary condition, right? But in decision tree, you can also get non-linear boundary conditions. Why? Like your question must be why and how? Because you can see in decision tree, we are not on, they're like we are not only focusing on into the probabilities which are occurring. In fact, we are drawing a tree to get even non-linear data, and also we can get some meaningful information out of that. We are not completely based on probabilities here. Like we are creating trees, branches, and there are many other things that you will understand in coming, like in future. So what next? Also, like I can tell you, like in decision tree can be upgraded. Like if this is a decision tree, you understanding decision tree, you can say it is there is a upgradation part of decision tree which is known as random forest. You can say if this is your bachelor's, this is your master's of the same thing. And if you are good with decision tree, you can easily upgrade yourself to random forest, which is these days very popular, especially with your, if you are doing projects on your Kaggle environment and all. Like if anyone have no idea about Kaggle, Kaggle is nothing but a website kaggle.com where it is completely based on data science, where you can, like you get a lot of data sets, data frame, projects to work on, to practice on. Even companies, they hire on the basis of Kaggle, like whatever, like they'll say if any company or any client have any issue coming up with their project and they are stuck somewhere, they'll just publish the project into Kaggle, and they'll rate a price like say 10,000, or let's say $1,000, anyone who solved this problem for me. So if you solve the problem ASAP and submit back to the person, you will get 10,000 $1,000. Like price varies, like even I have seen 25,000 price. Even you can work in a team and solve the problem, and you can submit that, and they'll see if everything is okay and very optimizedly you have like solved everything. They'll accept your solved project, and they'll provide you the money. Even if they like you, they can hire you. If you want, you can get hired with them, or not, you can, you can be a freelancer there, Kaggle. So basically, like Kaggle is nothing but a platform where you work on data science projects, and their random forest will be very helpful for you, and the basics of random forest will be coming from your decision tree. It is, and like if I want to say Kaggle in short, Kaggle is nothing but your like it's a competition forum for data scientists. Okay. Also, one more thing, like if this is a tree, and I've already shown you examples, and this is our trees. So the data which we provide here at the root node or the parent node, the data which we provide here is the test data. Now I think everything must be somewhat, the pictures is somewhat clear into your minds. Like if it's a test data, we are testing some of the other things and finally coming out with a result at the last. So this is a test data, right? Guys, please make a note. This is a very important part of data science. So I want you to make notes of all these. You can pause the video and make note, and then you can move forward. Okay, so I'll just erase this. Okay, so decision tree, I'll denote in short as DT. DT, decision trees are also like smooth with categorical values. if you remember categorical values in your logistic regression, there what we were doing in logistic regression, if there are categorical values, we have to do some or the other thing like dummy part, like one hot encoder or response encoding. Let me just write it down. In your logistic regression, if there are categorical values, what we do, we apply one hot. You must have seen in the project which I have solved. We must use one hot encoder, or there is a response encoding, like to solve it. Like logistic regression, we cannot directly solve the categorical values, and using one hot encoder and response encoding, it makes everything, like it increases the efforts. So wherever there is more human effort, there are more chances of getting errors. But in decision tree works really very well with categorical values. Very well with categorical values. So this is the one of the most important part of decision tree. Like we don't have to use one hot encoder or response encoding, nothing like that. We just have to assign the value and everything will be covered up. And also one more thing, in decision tree, usually there is a binary tree, like if this is my root node, and like this is 2 binary is 2, right? So there is a binary tree, but there are chances you can where you can even expect more than 2, like even you can expect 3 or 4. And then if this is the case, it's no longer binary, it is your multi-way splitting. So we say it's multi-way split. So if there are 2, this is your binary split, or we call it as binary tree. And if there are more than 2, we call it as multi-way split. Now let me just erase it. Okay, so let me just show you an example from a real data set from one of the medical domain. Because in medical domain, usually doctors, like I've shown you an example, he like keep on iterating us, like he keep on asking us, okay, so this has happened to you, so what you ate yesterday, and is there is a fever. So whatever the reply we give, yes or no, basis on the basis of that, in his mind he keeps on increasing the branches of the decision tree, and finally he comes with a value, right? I hope you're getting it what I'm trying to say. So again, I want to give you an example of a decision tree which is on based on a real data set of medical domain. So guys, if you don't know the value, like the terms, medical terms, that it's completely okay. You don't have to know the medical terms, but the thing is how decision tree works. I'm going to show you that. So in this data set which I have, and from which I will be showing you a decision tree, we want to predict whether the patient has a heart disease or not. Same thing which I have explained you, but it will be a little genuine decision tree having the real medical words or terminologies. So you can just ignore the medical terms here. All right. So I'll just make a decision tree here. This is something known as thal equals to 3. Paint type equals to 1 or 2 or 3. and this is something fluoroscopy colored. Thank God I'm not a medical student. Right, you must be seeing there are many such words, like even I can't even pronounce most of the words. So this is something like, if thal is yes and no, then I'll just draw it once and then I'll explain you. You can, like, it will take like 2-3 minutes. You can just forward the video where I have completely drawn it so that you can save time there. Yes, no. So there is no heart problem. If pain type is not among 1 to 3, so again you have to go for fluoroscopy colored, which is less than 0.5, and if it comes to be yes, so there is no heart issue. If it comes as no, there is a heart issue. I don't know what's happening here, but it's a good example to explain decision tree. No, yes. So there is a heart disease here. Here, enigma exercise as 0. Yes, no, yes. If age is greater than or equals to 51, why 51? They can even take 50. Okay, they've taken 51. So again, there is a subdivision. If yes, there is no heart disease. No, there is a heart disease. So guys, this is a complicated decision tree where you can see if what is happening here is, if something known as thal is equals to 3, like your doctor will check the reports and your thal is equals to 3, and if it is a 3, he'll say yes. So he'll check the pain type. If pain type is from 1, 2 or 3, the level of pain is 1, 2 or 3, yes, so there is no heart problem. If the level is more than 3, like it's not 1 to 3, it's more than, so no, then he'll go for fluoroscopy colored, and it is less than 0.5, and if it comes value as 0.5, so yes, like fluoroscopy colored comes to less than 0.5, so yes, so there is no heart disease, and if it comes more than 0.5, so there is a heart disease. And if thal is not 3, like the value is not 3, maybe less than or greater than 3, so a doctor will ask you to go for fluoroscopy colored, and it should be less than or equals to 0.5. If it is less than or equals to 0.5, he will ask you to do enigma exercise, and if it comes to 0, and if your age is 51, you have a heart disease greater than 51, and if it doesn't come to 0, so yes, you have a heart disease, something like that. So guys, I don't know what are the medical terms here, but this is a very good example of decision tree, right? Look, just ignore the terms and look at the tree. This is your root, this is your root node, this is your root node, and this here you will be providing your testing data. Your testing data will be entered here, and everything will now change. And this is how decision tree grows, and everything is taken care here. I hope everything is clear up to this, right? So you don't have to make a note of this if you are cleared with the decision tree in your mind. So basically this is how we come up to a final decision with the help of decision tree. So and those who are from like uh, coding background, any coding background, you can compare it to your if else code in any like Java, the if else, like if it is yes, go here, else go here, if else. So it is very similar to your if else coding, right? Those who can compare with that. All right. So I hope you are clear with the decision tree basic model structure, how it looks like. If you want, I can give you n number of examples like this. But I hope three examples which I have explained, from basics of the room, then easy doctor example, and then highest with all the medical terms. Decision trees can be more than bigger than this. Branches can be bigger than this as well. So stay tuned. You will be facing in a coding part, like maybe after two lectures, you will see a coding video where I have worked on a project of decision tree. It's a big project where each and everything is explained. I have explained so slowly and nicely that you'll having no doubt. But whatever I teach before the coding, the theoretical part is important. So you have to make a note in your into your mind. All right. So I hope if you are clear up to this, I'll jump to the next point, which is also the important point under decision tree, which is your homogeneity. Okay. So homogeneity is nothing but how to decide and divide which leaf will have what and how much. Like if this is a leaf, so after dividing, like which leaf, like how to divide, like what are the number of leaves possible and what values to be like stored here and how much values to be stored here. Everything comes under homogeneity that you will be seeing here. Okay. So if I want to give an example here, I can give, let's say, BP blood pressure is greater than 150. If blood pressure one greater is 150, so age less than 70, age greater than 70. So this value, like age and the value less than 70, and dividing into two parts, less than 70 or greater than 70, or maybe between 30 to 40, 40 to 50, or there is a third level 70 to 90. This is homogeneity. This we will be studying in under homogeneity how to decide and divide it. So here let me just open one more thing here. All right. So can I erase this, or I'll do it here? Okay. So there is a rule in homogeneity. There is a rule, or you can even say a pattern that has to be followed for accurate results. Like the results should be accurate here, and this after getting accurate results by following some rules, this everything is known as homogeneity. This concept, basically the concept is known as homogeneity. Now to explain you by giving example which I'm very good at. So let's say we have a root here and it is further divided into two parts. It has some circles and it has some crosses. Okay, so guys, you can see uh, these are in one leaf. there are only circles, and in another leaf there are only crosses. So here we can say homogeneity equals to 1, which is your maximum homogeneity. This is 1. So like you can, this is not possible in real life. It's almost in real world it is almost impossible to get homogeneity equals to 1. But if, like for perfect result we try to get h value very close to 1. So like this is very in real world scenarios or data sets which we will be doing, homogeneity equals to 1 is almost not equal. So 1 is max here, like almost not possible here. So you can also say this is your, if h equals to 1, this is your best homogeneity. This homogeneity you can call it as best homogeneity. Okay, so all right, so this is this. Now I must show you the real world example, how real world homogeneity looks like. All right, so in real world, if I want to take the same example, this can be the case. I hope you are clear now what I'm trying to say. In real world there can be some disturbances, or you can say noises, between the data sets which try to make homogeneity not equals to 1. Here homogeneity can be approximately equals to 0.9999, which is not bad, which is also good, but this is not 1, still not 1, the maximum value. So we cannot say it as is 100% homogeneous. I hope you are getting it, what I'm trying to say it here. And so this is not bad, like this is a very good homogeneity. If it is coming 0.9, it is very good indeed. Even you will not get such homogeneity. You will be getting like homogeneity as 0.81, 0.84 or 0.9, but 0.999 is a very good homogeneity. All right, so I'll just give you an example of bad homogeneity as well. Let's say this is a leaf. We have some circles. This is a very bad homogeneity. Very bad homogeneity. You can say homogeneity is 0.5 here, which is your, let's say, 50% homogeneous. This is 50% homogeneous. So whatever we do, we make sure that like just draw it here. What we have to do is if if we have H homogeneity here in your parent node, we try to make sure that homogeneity increases when we further divide it into leaves. So if H is here, we expect homogeneity should increase here. And how we do that? We keep a threshold. We keep a threshold as tau, a value of tau. We keep on checking that, like we fix a value tau, or named as threshold, and we keep on checking that if homogeneity what we are getting is greater than tau. If yes, if it's getting greater than tau, we just stop there itself and make it a leaf node. And like if it is greater than tau or equals to tau homogeneity, sorry, so we stop there itself. but if homogeneity is less than tau, then we again keep on splitting it until your our h increases to our previous value. I hope it is clear up to this. So this is basically nothing but your whole concept behind your homogeneity. I hope this is clear. Like whatever the value we have, let's say in our parent node we have homogeneity as 0.6. So we will expect in our child node our homogeneity is at least 0.6. Homogeneity is greater than 0.6, not even equals to. We expect 0. Maybe 0.62, 6 or 0.69 or 0.72. We expect a little higher homogeneity than our previous one. That's what I'm trying to say, and that's what how it happens, right? Clear up to this? And guys, trust me, like if you're not getting it into this theoretical concept, even I'm trying to explain, I'm going very slow in giving you examples, but when after these lectures of decision tree, there will be a project, and in the project, when you will be doing practicals like hands-on, everything will be completely cleared into your mind. Okay, so this is just the basic of what we will be doing in practicals. Okay, so I hope you have written this. So I'll just erase this. Now let me give you another example, not example, another concept, which is your Gini index. This is also important, I can say. Like entire decision tree is very important. So whatever the topics will be covering, I will be covering inside it. Everything will be very important. Okay. So Gini index. So what is Gini index? Gini index is nothing but it helps to decide what to choose for splitting. Uh, Let me just write it down. It helps to decide what to choose for splitting. Okay. So let me just brief you with one data set here. Let me just explain one data set here, guys. I want you to make this data set, whatever I'm like I'll be drawing now. I want you to make a note because there's a continuation of that, which in which I will be erasing everything from the screen so that you can look that into your own notes and compare the values, because the values will be gone if I'll erase the screen, right? So I just want you to like first listen carefully, make a note, understand, and then like after pausing the video and then play it again. So let me just explain you one thing here, one concept. I'll just draw it first. Yeah, I'll just like write everything. I would request you to you guys also write each and everything here with me. It might look complicated right now, but it is not at all complicated. Trust me. Okay, so this is what I want to explain. So this is nothing but a small data set which I have like shown like this, in which this part, the left part from this line, green line, the left part is your uh, your people less than age 50, and right side are the people greater than age of 50, and the top one are female and the bottom one are male. So this is nothing but this is a survey who loves to play football. Like I'll just write loves to play football. This is a survey on that. Or all right. So less than 50 age, if the if the person is less than 50 years of age and gender is female, so there are 10 who loves to like positive results. P is positive and is negative. So 10 loves to play football, 10 females love to play football less than age 50, and 390 does not loves to play football at all. And greater than 50, 0 females like to play football, and 100 they simply don't play. So nobody likes to play. And okay, so similarly with male, 250 love to play football and 50 does not love to play football. And at the greater than 50 age, wow, 50 people still plays football and 150 don't play football. So this is what our data set is looking like. I hope now you are clear up to this. Is not that complicated. So if I want to split it on the basis of gender, let's take females first. Females, uh, 10 females play football, 490, I'm sorry, 390 doesn't play football. Uh, no, no, yeah, it's 490, sorry. Yes, because if we are taking on the basis of gender, so we'll take entire thing, not age. On age, we will taking the this part only. So 490 doesn't play. So total we will have 500. For males who love to play football is 300 in total. You can see in males, you can see there are 300 in total who loves to play football, right? Like 250 plus 50, 300. And 200 doesn't play football. So your total is again 500. This is on the basis of gender. I want you to make a note of all this, because the next step, I have a note of all these things, but I will see from that and I'll do the rest calculation. But you should have a note as well to understand what I'm trying to explain here. So this is on the basis of gender. On the basis of gender, we ignore age. Now on basis of age, here we'll ignore the gender. Okay. So if the greater than 50, age is greater than 50, 50 people plays football, 250 doesn't plays football, so total is 300. If the age is less than 50, and 250 plus 10, 260. 260 plays football, 440 doesn't play football, and the total we are getting is 700 here. Alright, so guys, I want you to make a note of all this, because I'm going to rub this and then I'll explain one concept here, a formula on the basis of Gini index, which is also, the project is completely based on Gini index, which I will be working on. So I want you to make a note of all this. Okay, so I'll just erase. You can pause it. Okay, so now let's take the probabilities. Probabilities of, let's, female is obviously 1 by 2, because male and female, so probability is 1 by 2. And how to find the Gini index here? So there is a formula for Gini index, which is from I1 to K probability whole square. So what we do here is we look at the probabilities and square them up, nothing much. So I'll explain you how we split now on the basis of Gini index, or that too on the basis of gender. Now on gender, splitting on gender. On the basis of gender, let's split and put this into the formula. So Gini is probability is 1 by 2 for female, and 1 by 50. I hope now you understand why it's 1 by 50. You have to find the probability there from the back. That is why I'm saying that you have to have all the notes in front of you. So 49 by 2. This is, we are talking about females first, and then males. Probability is 50. 3 by 5. If you solve this, you'll get a value of 0.74. On this is splitting on the basis of gender. Now if I want to split on the basis of age, it will somewhat look like 0.7 260 upon 700 plus 440 upon 700 plus 0.7, so it will be 0.3. Together it makes 1. Probability is always 1. So 50 by 300 to 50 by 300. All the values I have written at the back in the previous page, so you can compare each and everything. You just know how to calculate the probability. So here if you solve this, you will be getting a value as 0.59. Okay, so here you can now here I think I should erase this page again. So Gini index on the basis of gender, I'm getting as 0.74, and Gini index on the basis of age, I'm getting as 0.59. So guys, this is how you calculate your Gini index, and after calculating your Gini index, you just compare which one is greater, closer to 1, and whatever the value is, obviously you will take that. So here we will be taking taking gender as my Gini index, and we will be splitting on the basis of gender only. And if you see the data set, what I have written, what I've shown you, I think I can go back. I'm not sure. No, it will take a lot of time. So like it is obvious, like we will be splitting on the basis of gender only, right? So age will not matter, gender will matter in this case, in our example. So this is how we will be doing Gini index splitting here. So it is easy, right? Not that difficult. You just know a symbol of probability, and you just have to find everything out there. So whatever the value is greater, you have to take that and you have to split according to that. Okay. All right. So guys, in next video, you will be seeing another concept, same thing, but in different way. It will be your information gain, which we will be using a lot of entropy terms, don't get afraid. Very easy, very, very easy. And a lot of things like this, entropy, and you will see like it is completely opposite to your Gini index. Like not opposite, you can say inversely proportional to your Gini index. And everything you will be seeing in our next lecture. So, and it is very important as well as interesting as well, the information gain part. So I hope it is Gini index part, the decision tree part up to Gini index is cleared into your mind. And if it is not, watch this video again and again, 2, 3 times, 5 times, 10 times, but make sure it is clear into your mind and then move forward to your information gain. Nothing is difficult. Like if you think it is something is getting difficult and watch it again and again, everything will be cleared. All right. So I'll just end this lecture here and you can move forward and go to information gain if you're clear with your Gini index. Alright guys, thank you so much. See you in your next lecture of information gain. Thank you so much.